Hello, my name is Samson Zhou, and today I will be talking about the sensitivity analysis of the maximum matching problem. This is joint work with Yuichi Yoshida. Sensitivity is a measure of how much a discrete algorithm changes when the input changes. For example, for a deterministic graph algorithm A, on a graph G that has n vertices, the average sensitivity of the algorithm is defined as the expected value of the number of edges in the symmetric difference between the output of the algorithm A on the input G compared to the output of the algorithm A on the input G minus E, where the expectation is taken over all edges E in the edge set of G. So this definition is a mouthful, and maybe it would be better illustrated with an example. So let's consider the case where the algorithm A is the greedy algorithm that outputs a maximal matching on a graph with 6 nodes. And suppose that this graph has the edge set that appears on the left side of the screen. Well, the greedy algorithm is with respect to some ordering of the edges. So let's suppose that the edge set has the following ordering. Suppose that we first see the horizontal black edge on the right side, and since it's the first edge that appears, then the greedy algorithm adds it to the maximal matching. Next, let's suppose we see the following black diagonal edge. And since it's already incident to an edge in the matching, the blue edge, then the black diagonal edge will not be added to the maximal matching. Similarly, the greedy algorithm does not add the third diagonal edge to the maximal matching. The fourth edge is not added to the matching, and so forth. Now, when the last edge appears, it is not incident to any edges that's already in the matching, and thus it's already added. It's also added to the matching. So, for this graph and the ordering that we showed previously, the maximal matching returned by the greedy algorithm will be the 2 blue edges on the right. Now let's suppose that we have the same graph, but the first edge, the horizontal black edge, is removed. And let's suppose that the ordering of the remaining edges remains the same. Now the greedy algorithm will add the first diagonal edge, and it will also add the second diagonal edge to the maximal matching. The next 2 edges will not be added to the matching, but the final edge will be added to the matching as well. Thus, in the first case, the maximal matching returned by the greedy algorithm is the 2 horizontal blue lines. Whereas in the second example, the maximal matching returned by the greedy algorithm is the graph that is in the lower right. Now, the symmetric difference between these 2 graphs is indicated by the edges in red. Thus, the symmetric difference has cardinality 3. Now, the average sensitivity for the greedy algorithm repeats this analysis averaged over all edges E that's in the graph. Again, the sensitivity is a measure of how much a discrete algorithm changes when the input changes. But this definition that we described previously is for a deterministic algorithm. For a randomized algorithm, the average sensitivity is defined as the expectation of the Earth mover distance between the output of the algorithm A on the input G versus the output of the algorithm A on the input G minus E. And we consider this quantity an expectation over all edges E in the edge set of G. This definition is well motivated by a number of applications, and the first one we'll consider is a situation in which we have a number of clients on the right that demand service from a number of servers on the left. Suppose that we have some possible routes that connect the servers to the clients. We want to form a matching to give as many clients service as possible. Thus, we choose some matching on this underlying network. And this matching is indicated by the edges in blue. But now suppose that another edge arrives. This is indicated by the horizontal black edge at the top. We still want to provide service to as many customers as possible, so we choose a new maximal matching. In this case, we choose the horizontal blue edges. But the symmetric difference between the first matching and the second matching is actually the entire network. And thus, if we need to build some infrastructure to support the connection between the clients and the servers, then we have to rebuild this infrastructure completely when we obtain a new edge. Thus, it is advantageous to consider an algorithm that has low sensitivity, meaning that when a new edge arrives or an old edge is deleted, that the infrastructure needed to maintain the matching between the server and the clients is minimalized. Average sensitivity for graph algorithms was first considered by Mirai and Yoshida for the quantity centrality. They analyzed how much quantities such as centralities for page rank, betweenness centrality, and so forth changed when an edge in the network was deleted or added. Here, centrality is a quantity that roughly measures how important a vertex is in an underlying network. Subsequently, Varm and Yoshida considered the average sensitivity for a number of graph algorithms that output edge and vertex sets. They considered the problems of minimum spanning forest, global minimum cut, maximum matching, vertex cover, and so forth. Hung and Yoshida also considered the average sensitivity for spectral clustering. Namely, they gave a number of algorithms with sensitivity that depends on the eigenvalues of the. In this work, we introduced the definition of worst case sensitivity rather than average case sensitivity. Whereas the average sensitivity is defined with respect to the expectation of the Earth mover distance, the worst case sensitivity is defined with respect to the maximum distance between the output of the algorithm A on G and G minus E across all edges E and the underlying edge set. We first give a 1 plus epsilon approximation to the maximum matching problem with worst case edge sensitivity O of 1, where here we suppress all dependencies on epsilon. We'll also talk about a deterministic algorithm for maximal matching with worst case sensitivity delta to the x, where x is this quantity here, and delta is an upper bound on the degree of the vertices in the underlying graph. So we'll first talk about the 1 plus epsilon approximation algorithm. And notice that our result improves upon a result of Varma and Yoshida that give a 1 plus epsilon approximation to the maximum matching, but has average sensitivity in this quantity as follows. Namely, opt here is the number of edges in the maximum matching, and it can be as large as n. So they give an algorithm with average sensitivity roughly n over epsilon cubed. And this is average sensitivity, whereas we give an algorithm that gives a 1 plus epsilon approximation, but has worst case sensitivity O of 1. So not only do we improve upon the sensitivity, but this is the average sensitivity versus the worst case sensitivity. Now this can be difficult because the previous example illustrates that the greedy algorithm can have sensitivity omega n for maximal matching. Recall that just by adding a single edge, we can force the maximal matching by the greedy algorithm to entirely change so that the sensitivity, the symmetric difference, is actually the set of all edges in the graph. Fortunately, we first show that for a randomized greedy, we can have an analysis that shows a much lower sensitivity. So in the randomized greedy, what we'll do is first randomly choose a permutation of the edges in the graph, and then we'll run the greedy algorithm on this permutation of the order. The idea is that the expected deleted or edited edge should appear at roughly halfway through the ordering of the edges. And this seems kind of bad, because if it only appears halfway through the ordering, then maybe we'll still have sensitivity omega n. But the intuition is that most of the edges in the matching either occur early in the ordering, if the underlying graph is dense, or the added or deleted edge does not affect many other edges in the matching if it's a sparse graph. Formally, if we let pi of e for an edge e be the rank in the underlying ordering that we choose, then we define I sub pi of e to be the neighbors of e with smaller rank than e. Now it's clear that we have an invariant that shows that if e is in the maximal matching, then it can only be the case, if and only if, that no edges of I sub pi of e are in the matching. Now we want to consider the set S of edges that must be modified to maintain the invariant if an edge e is moved to the beginning of pi. So this is our sensitivity analysis, where we show that e is added or deleted. But actually, we show that we can consider the case where e is moved to the beginning of the permutation. Now, unless pi of e is equal to the minimum of pi of s, then no edges need to be modified. This is not obvious, but it can be shown with a bit of work. It can also be shown that pi of e is equal to the minimum of pi of s with probability 1 over the size of s, and thus the expected number of modified edges is O of 1. So this analysis is a bit evolved, but similar ideas were previously used to show an algorithm for Maximal independent set in the dynamic distributed setting by Sensor-Hill et al. So now we have a toy subroutine that shows that the randomized greedy for maximal matchings with worst case sensitivity of 1 can be used as initial procedure. And our goal is to go from maximal matching to 1 plus epsilon approximation algorithm for maximum matching. One possible approach that also extends from a maximal matching to a maximum matching approximation algorithm is the multi-pass streaming algorithm of McGregor. The streaming algorithm of McGregor uses a layered graph that creates a graph with L plus 1 layers that simultaneously sample a large number of augmenting paths of length L. For example, consider the left graph that has a maximal matching M with 2 edges in an augmenting path of length 3. Then the corresponding layered graph, if we are only interested in augmenting paths of length 3, will have 4 layers. The first and last layer will have vertices corresponding to each vertex in the graph on the left, and the middle layers will all have vertices corresponding to the edges in the underlying graph. Thus, we see that 1, 2 is an edge in the graph on the left, and the vertex corresponding to 1, 2 appears in both the layer 1, L1, and L2 on the right. Now, the layered graph randomly chooses edges between vertices when there are edges present in the corresponding graph on the left. This induces a number of augmenting paths, and thus we can sample a large number of augmenting paths from this layered graph. Now we'll terminate this procedure in roughly 1 over epsilon iterations so that we have all augmenting paths of length 1 length 2, length 3, all the way to length 1 over epsilon. We'll sample a number of augmenting paths from each of these lengths, and thus we've achieved augmenting paths of length up to 1 over epsilon. And this is enough to get a 1 plus epsilon approximation algorithm for maximum matching. Now we'll do this roughly k times, and thus we'll get roughly k augmenting paths. And k here is some quantity that's independent of n. It's only dependent on epsilon. Now we do this k times, and it can be shown that in the first step, our sensitivity is at most 3. In the second iteration, these 3 edges can further affect at most 3 times 3 edges, which is 9. And arguing inductively, we see that the worst case sensitivity is at most 3 to the k, which is still order 1 when we suppress dependencies on epsilon. Moreover, our runtime is roughly n plus m, where n is number of vertices and m is number of edges, times k. So this is our linear time algorithm that gives a 1 plus epsilon approximation to the maximum matching problem, and it has worst case edge sensitivity over 1. Next, we'll talk about a deterministic algorithm for maximal matching with worst case sensitivity delta to the x, where x is the quantity here, and delta is the largest degree of a vertex in the graph. Our deterministic algorithm uses 2 ingredients. The first ingredient is a deterministic local computation algorithm by Cole and Mishkin that produces a 6 to the delta coloring of a graph with degree delta. The LCA uses delta times log star n queries and has the property that the LCA only queries vertices within distance log star n. So to get the coloring of a node, the LCA will look at the colorings of adjacent nodes. Then it'll look at nodes that are adjacent to the adjacent nodes and so forth, but only query vertices that are within distance log star n. At a high level, the algorithm partitions the graph into forests and assigns each vertex a color based on the least significant bit that differs between the node ID and the parent ID. The second ingredient that our deterministic algorithm will use is a framework by Parnas and Ron that simulates local distributed algorithms using deterministic LCAs with delta to O of C probes, where C is the number of colors that we use. The framework iterates through colors and adds each edge to a maximal matching if no adjacent edge is already in the matching. One can think of this algorithm as a greedy algorithm, where we first produce a maximal matching with respect to the greedy paradigm, but then we iterate through the colors and repeat this paradigm on the pre-built maximal matching at each step. The key property we'll use from this framework is that only queries vertices within distance 6 to the delta. So combining these facts, we have a deterministic LCA that queries vertices within distance log star n, and a framework that queries vertices within distance 6 to the delta. And by considering a tree analysis, one can show that the sensitivity is at most delta to this quantity 6 to the delta plus log star n. This is because this is the number of queries in the LCA that can be affected by a single deletion or addition. We can show this by starting at a root of a tree and proceeding downwards. So this gives both our 1 plus epsilon approximation algorithm to the maximum matching problem and our deterministic algorithm for maximal matching. We also show in the paper that any deterministic algorithm that gives a constant factor approximation for the maximum matching problem has worst case edge sensitivity omega log star n. We show this using Ramsey theory and also note that our worst case edge sensitivity also applies when both vertices and edges are deleted from the graph. We also give a theorem that shows that any graph with edges bounded by w, which is some quantity that is polynomial in n, we can find an algorithm that outputs a 4-alpha approximation to the maximum weighted matching problem, where alpha is a trade-off parameter. Namely, for alpha equals 2, the algorithm has weighted sensitivity w log n and normalized weighted sensitivity log n. For alpha larger than 2, the algorithm has weighted sensitivity of w and normalized weighted sensitivity of 1. Here, weighted sensitivity is a natural generalization of edge sensitivity that we introduced in the paper. Because our paper is the first to consider worst case sensitivity, we believe there are a number of interesting future directions that we can study. Already, there has been analysis of worst case sensitivity for monotone submodular maximization by Maximal and Yoshida. But we can also look at worst case normalized weighted sensitivity for other graph problems. Another interesting question is whether there exists constant factor approximation algorithms for maximum weighted matching with low worst case sensitivity. Finally, we can consider whether there exist 1 plus epsilon approximation algorithms for maximum weighted matchings with low worst case normalized weighted sensitivity. For full details, refer to the paper, and thank you for listening to our presentation.